Welcome to another class of analysis of Boolean functions, and today we'll be talking about the sensitivity conjecture. Okay, let me share my screen. Okay, so we'll be following the paper called Induced Subgraphs of Hyperkeys and a proof of the sensitivity conjecture. And this is a paper 1 of, I guess, 2019. And basically, this is, well, it's a proof of the sensitivity conjecture, which we stated in the previous class. But let me just recall you what is sensitivity. Versus block sensitivity. So I give you a function, and for this class, I think in most cases we use this 0, 1. So I give you some Boolean function, and sensitivity of f, just to recall, is the maxima, the worst case scenario, over all x. Okay. For some reason, again, it stopped showing. Okay. So you take a worst case scenario of what? Of sensitivity of f at x. And what is that? Where this guy here is the size of the I from 1 to n, such that if you flip I, this is different than the value of f at x. Okay. This is sensitivity. And block sensitivity, again, just recalling what we did in our last class. And then block sensitivity is, again, taking worst case scenario. However, instead we have block sensitivity at x of f, and this quantity is the size of, say, another maxima of, say, t, where we have, say, block B1, B2, disjoint union of t blocks, and such that f of, and if you flip all guys in each block, say I, in x, that's different from the value of x. And so you take the largest disjoint union of blocks, largest in terms of the maximum number of different blocks you have, the quantity of blocks you have in this union. And if you have the property that if you flip the entire block, for each block, if you flip the entire block to get a different value, then you account for that, and then you take the maximum over all the t. Okay. And so there was a long-standing question: is sensitivity related with block sensitivity? Conjecture: is block sensitivity less or equal than sensitivity raised to a certain constant? And then of course that from this definition, and we saw that in the previous class already, that sensitivity is less or equal than block sensitivity, because since I'm taking worst case scenario, I could take the blocks to be just a single element, exactly those elements coming from the block of the sensitivity of x at the point x. And that would be an admissible T, would give you exactly sensitivity of f at the point x. And so since I'm taking worst case scenario, this will happen, okay? And then this is now a theorem. This is a theorem of Huang. That's the sensitivity conjecture. Solving the sensitivity conjecture. Which is, so this is a paper in the Annals. And as a corollary, we have the sensitivity conjecture, because we have a result of Nizan and Zaghi. And if you pair that with the result of Huang, what you get is that, well, block sensitivity is less or equal than twice the degree of f squared, and that's less or equal than twice sensitivity of f to the power 4. Okay. There is actually a paper that improves this result of Nizan. This is Nizan Zaghi, and this is Huang. And there is actually a paper that removes it too in the Nizan Zaghi result. So you actually have it without these two. But anyway, we proved only this one in our class. Okay. And what is this thing related with induced subgraph hypercubes? Well, basically, the idea is that, well, the function f can be seen as a coloring of this set here. And you can think this set as a graph. So you can think f as a coloring of that graph. Okay. So in that way, the induced subgraph would be the values, the x's where f is 1, for instance, or the x's where f is 0. Okay. And that's the relation here. That's what's going on. Okay, so let me define the edges of our graph. Well, the idea is not new, it's actually pretty old, which says that x, and I will use this notation. This is an undirected graph. So if I connect it, if x is connected to y is connected to x. So say, I would say like this: if x is a neighbor of y, if and only if the distance, which is the Hamming distance, the number of indexes where they differ is exactly 1. Okay, so for instance, if you say that a point is even, if the sum of the coordinates is even, and if you say that a point is odd, if the sum of the coordinates is odd, then an even guy can only be a neighbor of an odd guy, and so on. And for instance, you can see that if you consider even. So this is a bipartite graph, because if you consider even, you see the axis here. And again, F2 here is just fancy notation for, just call F2 here, it's just fancy notation for 0, 1. And because sometimes we use the group properties of F2, identifying with integers modulo 2, and sometimes we do not. And so just keep that in mind. So even is a set of nodes of size 2 to the n minus 1, of course, and has each guy is completely isolated, has no neighbors, because, well, I can only be a neighbor of an odd guy if I'm even, and so that's why it's a bipartite guy. It's the same with odd. Okay, let me define another thing. So if G is a graph, then and X is in G. So imagine G is just a subset of F2n, but in general, it could be any graph. Then we denote by Px is the degree of X, which is the number of neighbors. So okay, so that's the degree of X. And then the degree of a graph, so we write like this, is the maxima of the degree. Okay. And well, okay. So how many degrees? So yeah, so now we have a graph, and this graph has 2 to the n vertices. How many edges does it have? Well, it's a simple computation, actually. You can just pretty much choose n minus 1 guys. If you fix an x, you can choose n minus 1 guys and then change another. And there's any position to change another. And so these are the number of edges. And if there is a result, a node result, this is from 1988. The year I was born, actually. It's a result of Huang, Graham, the famous Graham, famous. They show the following. So imagine now that you have G as a subset which has more than 2 to the n minus 1 points. So it cannot be the even guys or the odd guys, okay? Has to be a bit more. Then the degree suddenly jumps. The degree was 0 before, for instance, for the even guy. But if you just add 1 guy, you must have at least degree log on base 2 of n minus a half log of n plus a half. And they constructed a G with g greater than 2n minus 1 and degree strictly less the square root of n plus 1. Okay, so they are saying here that, okay, although you need to have that thing, there is a guy which can be pretty big. You can only, actually, we will show later that this guy they build actually have degree equal to the ceiling function of square root of n. Okay, well, the degree would be comparable to square root of n. Okay. So Huang's result, we will show that actually this bound is sharp. Okay. So this is their result. We will show this thing, this first item here. Sorry, the second item here in a moment. Let me just present Huang's result. Huang's result term. He improves this first statement. He says that if g is greater than 2n minus 1, then actually degree of g is greater or equal than square root of n. So that very much improves this, and also it shows that this, maybe put the note here. It shows that this G naught they construct is sharp, because in their paper they actually pose that perhaps they couldn't show that this bound was sharp. They show, well, perhaps by slightly changing our proof, we can make this guy much less than square root of n, maybe like epsilon times the square root of n, press some epsilon very small. And that's actually false. You can't do it by Huang's proof. That's the low bound. And so their construction was actually sharp. So that's what, and we will see that in the construction in a moment. So this is Huang's result, and how all these things connected, how the sensitivity conjecture is solved by Huang's result. Well, that we can solve very quickly, actually. And this is a result which was already known of of Gottsman and Lineal. They show that let H R be increasing, but let's say non-decreasing. Non-decreasing, I think it has to be increasing. So suppose you have some increasing function. The following are equivalent. A, for any subgraph with data has less than 2n minus 1 or more than 2n minus 1, then the maxima of the degree of G or the degree of the complement of G is greater or equal than Hn. So suppose you have that. That's equivalent to say, so for every graph you have this property. It's the same to say that for every Boolean function, we have f of f greater or equal than h of the degree of f. The sensitivity of f is greater or equal than h of the degree. And we will see the proof of this result in the end of this lecture. but you can already prove our main result. So note, so let's say first note. Let's say first observation. That this improves, so we obtain, let's say, theorem star. Let me give a name here. Theorem star, and if we obtain theorem star, then we obtain the sensitivity conjecture. Because the sensitivity conjecture is about this, and we got power 4. And there's still work going on in this. I think people believe that the correct exponent here should be 2, and we have power 4. So this is still, people are still working on that, but that seems a bit harder. Maybe it's possible. Maybe we see in the next 10 years somebody proving that. But that's like beside the point. Like the most important thing here from the computational aspect is that these two measures of complexity are polynomially related. So how do we obtain theorem star? Well, it's simple now because well, you just apply Huang's result. Huang's result says that we always have that if the graph has more than n-2 vertices. Well, if this guy here has different than n-1, but either it or its complement has more than 2 n-1 vertices. So and so for one of them, you'll have this found. So you can take h to be square root of n. So say, I put 2 stars here. By theorem 2 stars, we can take h of n to be square root of n. And so we have that the sensitivity of f is greater or equal than the square root of the degree of f. And that's it. That's what we wanted. Okay. And the second observation is that theorem star is sharp. And why sharp? Because, well, we just said it, by the Shun, Kuretti, Graham, and Seymour result, they constructed a guy. So let's see that construct. It's actually a nice construction. We were doing generality as they do in the paper. However, in the end, we will just take a very simple case of this more general construction. They do in generality because, again, they thought they could actually improve and make the construction of this graph with a size much less than square root of n, which is not actually possible. But anyways, okay, so to do the thing, we will do a certain identification. We will identify this set with the subset of n, okay? And the identification is simple. Each x is mapped into the set xx, which is the set of j's such that xj is 1. Okay, that's a pretty simple identification, and you see that x and y are neighbors if and only if you look at the symmetric difference between these two sets, this is exactly 1. Okay, so two sets will be neighbors if and only if they differ only by one element. I mean, they differ exactly by one element because x is not neighbor of x. Okay, so now to create, if I want to show that this is sharp, what I have to do I have to construct a graph of size. We actually construct a graph of size 2n minus 1, 2 to the n minus 1 plus 1 that has degree less or equal than square root of n plus 1. So that would show that this bound, this lower bound is sharp. It's the best you can possibly do. Okay, so how can we do that? That's simple. So consider, it's a very tricky, I mean, sort of a sleight of hand construction. It's nice. So let's just, let's say it's like Fj be a family of subsets of n. So each Fj is just a subset of n. And you consider, say, x of x to be the subset of n, such that the size is even, and there exists some Fj contained in F, or you can even write here, or, so this first, or F is odd, and there is no Fj contained in F. Okay, so you're even, and there is some set contained in U, or not. You're odd, and there is no set which contains. And then they define this R of F to be the maxima of the Fj's of the size, and this T of F to be the maxima of the T's, such that there is this Fi1, Fit, and there exists, say, Li1 contained in Fi1. There exists Li2 contained in Fi2, and so on. Lit contained in Fit, and Lij is not contained in Fik if I is not k. Okay, so in a way you can find subsets in this collection F, such that each one contains a set has a member which is not in any of the others. That's it. So a collection of sets, each one has a member which is not contained in any of the others. And the maximal collection of sets you can make of this with this property, the size of this maximal collection is T. Okay. And then the claim is that so if you consider X as the graph itself, this is a collection subset. Subsets now have neighbors. They have vertices, which is a set is connected to the other if they differ exactly by one element. And so you can consider this as a G, and you can ask what is the degree of this graph G, and they say that this is less or equal than the maxima of R of F and T of F. Okay, so let's see how. This is actually pretty simple proof. Well, let F belong to this guy and this guy even. Okay, so if say S is connected to S prime, so they differ exactly by one element. Well, S prime, then S prime, again, S prime has to belong to, let me even write here because it's a neighbor. Then you must have that S prime is contained in S. And of course, S prime is odd. I mean, it has to be odd. And it has to be contained because, well, the only other possibility is that I have, because you can either add an element to S or remove an element to S. These are how you create neighbors of S. So if you add an element, then S prime would contain S. But S has containing itself a set F. While if you're odd, you cannot have any F. So it has to be this way. Okay. And so you get that S minus S prime is just some element L prime, and L prime belongs to some F in the family, say some Fj. Okay, so now if you have, say, S2 primes different than S prime, and this is another neighbor of S, then you have the same situation. Belonging to some, I don't know, to some other F, Fj, Fl, no, not a good letter. Say, let's say F1 or F2, something like that. Okay, but then what you realize is that the claim is that these guys must be different. So what I want to say is that for each guy which is a neighbor, you can associate a okay, no, let me go back. That's not what I want to do. We could do that way, but that's too complicated. So, okay, so it belongs to, let's go back. Okay, so you have this, and you have that this guy belongs to F1. That's not what we want to do. All you want to do is the following. Is the following, that if we have some other set F2 prime, that then you must have the same condition that we derived before. And then and L2 primes must belong to the same F1. Okay, and must be different than the guy before. Okay, why is this true? Because look, well, first of all, this set here is different. So if this guy is different from this guy, okay, well, S prime is just S minus L prime, and then S2 prime is just S minus L2 prime. Okay, and so and I know that F is contained in S. So this is the guy, people should say F even So there exists some F, let's say F1 contained in F. Oops, what happened? Okay, technical problem. So basically, let me go back here quickly. It should be the following. So you take F, so there exists, say, S and S even. So there exists some F containing F. Okay, that's what we know. Now, if S prime is a neighbor of F, then you know that this has to be true. Now, this L prime has to belong to this F1. That's the claim. Because if it didn't, then, well, F1 is entirely contained in F. If the only difference you have from S prime is not in F1, then F1 is also contained in S prime. And that cannot be the case. So L prime is there. And then if S2 prime is another set, and S2 prime is different than S prime, then again, this guy has to belong to F1, and it has to be different. Otherwise, it wouldn't be different from S prime. Okay. And so, so you conclude, to deduce that for every neighbor, you have a unique element from F1. So you deduce that the degree of F is less or equal than the cardinality of F1. And so the degree of F is less or equal than R. I guess we define that as R of F. It's the maximum number of the F's in the family here. Now, if F is odd, and say S prime is a neighbor of F, then, well, of course, S prime is even, and S has to be contained in S prime, and there will be then some F prime in the family, F prime contained in S prime, and therefore S prime minus S must be some L prime, which is an element of this family. Because F prime cannot be contained in F. And the same for another guy. If F2 primes is a neighbor of F, then you have the same thing. F2 primes minus S is some L2 primes, and that's contained in some member of the family F prime prime. Of course, that L2 primes is not in F prime. Why? Because if that was the case, otherwise, well, F prime minus L prime is definitely contained in F. But definitely contained in F. However, then, well, L2 prime belongs to F prime. You didn't remove it because you removed L prime, and L prime has to be different of F2 primes. Otherwise, the two sets S prime prime and S prime wouldn't be different. Okay, we're assuming that you're taking a different guy. Yes, so we have to assume that this is different than S prime, of course. And so L2 primes would belong to F, which is impossible because it's outside S. Okay, so in that way, so for every f prime related to f, you can associate an element of a set f prime in the family and an element L prime in there, such that this L prime is not in all the other L primes you can build up by selecting neighbors of f. Okay, so that's exactly the TF condition we defined before. And so we conclude that the number of neighbors, the degree of f, is less or equal than R of f. Okay. And so we conclude that the degree of f is less or equal than the maxima of R of f and T of f, because it could be even or odd. Okay, that finishes the claim, and that pretty much almost like solves everything, because now we just have to apply a counting argument. So now, so what do we have so far? So we have this family of subsets, and we create a graph. And we do know that the degree of this graph is bounded by that. So now let me count. We want to estimate this, because we want to show that this is 2n minus 1 plus what? So how do we do that? So first of all, so if you get a set even, f even, so say fix f in the family you choose, and you look for the subsets which are even. Even here means that the number of elements in the set is even, and odd here means that the number of elements in the set is odd. And that's exactly in a match with the previous thing we defined here. Yes, if that is even, you can use the sum of the coordinates of the vector is even, which translates to the number of elements in the set. And if I look all the sets even that contain this particular set F, what's this number? Well, it's easy to deduce, and we'll leave as an exercise. This is what happens. It's 0 if you have cardinality n, and n is odd, and 1 if you have cardinality n, and n is even. Because we want to know the sets F that contain my set F. Well, but this guy has to be even. So if you start with F, and F has 10 elements, and n is 100, well, I can prescribe the order 89, but then I have to either select one element or not to make the set even, because it has to have size, to have an even size. Okay, and so basically it's half is a half of 2 to the n minus the cardinality of that. Okay, because these are your degrees of freedom, and to select, and so choose to that degrees of freedom, because you have all the possible sets of that cardinality you can add to your previous set F, but you also have to make it even. And if the guy has already, if F is of size n, so it's everything, and n is odd, and so there is no even set that contains it. And if, oops, sorry. And if F is even itself, then F contains itself, because Okay. Equal here as well. Contain be equal. I use contain as symbol to be contain or be equal, not strictly contain. In any case, this formula is easy to deduce. And for the odds, it's the same, more or less. And these are exactly the same. So we call this function here h even of cardinality of f. And we call this function here h odd of the cardinality of f. Maybe h is not a good name. Let me put, say, let's say, R. The R dot dollar. Let me put P. Okay. So what's the cardinality of this set? Well, it's simple. You can just use the inclusion exclusion principle, which is, I'm just going to, because if the guy is even, so recall that I'm selecting guys, even guys that contain one set. So maybe you contain one set, or maybe you contain two sets, or maybe you contain three sets, or maybe you contain four sets. So you add up all the guys that contain one set, and then you subtract all the guys that contain two sets. Oh, yeah. And then you add all the guys that contain three sets, and so on. This is the first sum. And then you have to do what? Then you have to look for the odd guys. The odd guys cannot contain anybody, which is the same to say that I'm taking all the odds and I'm removing the ones that contain somebody. And so it's the same game here. And now with the function odd. And so this is 2 to the n minus 1 plus or minus, depending if n is even or odd. And then in here, it would be just what? F in F. So note that if I subtract these two functions, the only difference is that I'm gonna get this minus this. I'm gonna get a +1 if n is even, and I'm gonna get a -1 if n is odd. That's the only difference. So that's where this plus or minus come from. And now this is just the function 1. And only when the set has cardinality n, exactly, because this is the difference. And so it's going to be this, and then minus f prime, where the union has cardinality n. Okay. And that's it, pretty much. You can't do anything else. And then when you do, well, depending on the choice of the family, this function can change. Okay. And you do want plus or minus here. And then recall that if I prove that this is 1 in some case, then if perhaps I give n here when n was odd, and then I get -1, then I just take the complement of that set, and then I will create something with 2n minus 1 plus 1. Okay, so that's fine. Okay, but the point is, if f is a partition, then this sum here is then this sum here is actually easy to compute. And it's just, I will leave it as an exercise. This is just minus, yes, this is just plus minus 1 n plus k plus 1. It's a, say, k partition. It's a partition of k sets. Okay, then that's it. And well, I can definitely partition, oh, it's a partition, sorry, of n. But definitely can partition this, I mean, it's a partition of 2 to the n, of course. These are, oh, sorry, it's a partition of n. Then you have that, of course, it's a subset of n. And so, but clearly I can partition n as a disjoint union of k sets where k is as close as I want to square root of n, and each set also. So you just take the first square root of n guys, then you take square root of n plus 1 to twice square root of n, and you do that. You have to do that square root of n times to have square root of n sets, all of size approximately square root of n. Basically, that's the construction. Okay, and so if that is true, then you conclude that x of f, the size, is actually equal then, oh, sorry, the degree of x. We just computed, that was the claim. The degree was less or equal than the max of what? R of x and T of x. But R of x is what? This is square root of n, at most square root of n plus 1, less or equal, because this is the size of its stack. And T of f is the maximal disjoint construction we can do. Well, this is the partition, so the maximum is k, and that's also bounded by square root of f n plus 1. So this is less than square root of n plus 1. Okay. Pretty much, and sorry, and so this is pretty much what you can do, and then that's it. You have proven the claim, the construction. This is the construction. So what we did was we did the general construction where we estimated a number here, and we estimated the degree by this lemma, and then by just taking a simple choice of subfamily f, that gave us a set of size at most square root of n plus 1, and also the size of x is what? 2n minus 1 plus this guy. So either this is 1 or minus 1. In any case, either you take x of f or the complement, and that will give you the construction. And so yeah, no, I guess you can't take the complement, otherwise you may screw up with the degree. So probably what you have to do is not taking the complement. So if that guy is minus 1, you just slightly change k by k plus 1 or something for you to make plus 1, still within this range. Okay. I guess, yes, I guess that's what you have to do. And then you construct, let me put 2 hours here, then size of x is 2n minus 1 plus 1, and you also have that. And that here is to pay attention because you have to select k in order to make that one. Okay, but in any case, that's doable, and that's proving the sharpness. Okay, so now And this is the construction that say that, oh, maybe we can select a better step F, so that to make this much smaller than square root of n. That's actually false, because Huang's results show that this is always greater or equal than square root of n, so not possible. Anyway, let's now prove Huang's results, and then in the end we prove the Gottman-Lineal result. So let me prove theorem 2 stars, which is this result. Okay, this is actually not hard. So let me, okay, so suppose you have a graph. If you have a graph, you can get the adjacency matrix of the graph. And this is the adjacency matrix of the graph. That is, you put 1 in the matrix, so the columns and the rows are enumerated according to the elements of your graph. So you could put any graph here, and you put entries, which would be 1 if the points are connected, the vertices are connected, and 0 otherwise. Okay. So that's the adjacency. Adjacency matrix G of F2, and but you can see that this can be done with any graph. And so if G is a subgraph, then AG, which will be again the adjacency matrix of you can see a subgraph as a sub-principal matrix of the adjacency matrix of the graph that contains this graph. Okay, so I could define the same way a matrix with the columns and rows numbered by the vertices, the vertices of G. But similarly, I could just take a submatrix of this larger matrix. So I just again take the same edges matrix, but then I just impose that these two guys belong to G. Okay. Okay, so that's one thing. And then, so this is two things. And then there is let's say, a small claim which is already known, actually. It's proven in the paper, but it's sort of it's already known in graph theory, that, and this is in general result, if G is a graph, and say, and you have A of G, its adjacency matrix. So let's say, let G be a graph and G is an adjacent matrix. And let's say AG of V, because lambda V for some V different than 0. So you have some vector, some eigenvector. Okay, then what do we have? Okay, so let's say, well, V would be a vector numbered by the elements of the graph, and so then you can say let Vx be the supremum of Vx. By the way, A, this is an indirect graph, is a symmetric matrix because if X connected to Y, Y is connected to X. So the eigenvalues are only real and the eigenvectors are all real. And so here I'm just taking the moduli real numbers, okay? And so let's say M be the maximum of this guy. So what you do is that you have what's a lambda times M is what? Is just AG times V, and then you take what is coordinate X naught. So suppose that V of X naught is this guy. So let me put it down. Okay, and you take moduli. So what is that? That is summation of X, that is summation that one is X is a neighbor of Y, of Vy, and this is X naught, and I'm summating over all the Y's, oh, sorry, this, yes, so it's all the Y's in G. That's it. But then what you can do is that you can bound this just by the maxima. So you put f of X naught, which is the maxima, moduli, and then you have the sum of these things, which is the degree of X naught. And so you conclude the moduli of lambda is less or equal than the degree of X naught. And so you conclude the moduli of lambda is less or equal than d of G. And so you conclude that the maxima of the moduli of the eigenvalues bounds from below the degree of the graph. Okay, that is what we did here. However, we can easily modify this lemma for our purposes, which is the following. Instead of considering AG, let me see here, claim, second claim, you see, tilde, which is the same is true, meaning delta G is greater or equal than the max of the moduli lambda is an eigenvalue of AG, but now tilde, where A tilde G is the matrix theta xy, 1 of X, xy, and G. And theta xy is just some real number between -1 and 1. But it could be anything. But the same proof holds because, well, you do the same thing, you do the same trick. When you get up to here, now you have the thetas here. So then you just brutally bound everything, and this theta is always less or equal than 1. Then you brutally bound by the degree, and there we go. Okay, so I am allowed to put plus or -1 in the entry. So I'm allowed, so there is a sort of optimization game here. You just put thetas between plus or -1, exactly when X is connected to Y in the graph, and you try to maximize the eigenvalue. That would give you a better bound for the degree, better lower bound. Okay, that's claim tilde. Okay. And the final thing we need is what's called Cauchy's interlaced theorem, okay, which is the following. If M is a symmetric matrix and say K by K, symmetric matrix, and say M tilde is L by L symmetric matrix with L less or equal than K, then if lambda 1m greater or equal lambda 2m greater or equal lambda km, the eigenvalues of m and lambda 1 m tilde greater or equal lambda L m tilde, eigenvalues of m tilde, then the interlaced theorem says that lambda I of m is greater or equal than lambda I m tilde, which is greater or equal than lambda I plus k minus L m. Okay, there is a monotone property in the eigenvalues. This is reminiscent of the minimax results in linear algebra. I won't prove this result. You can Google it. It's accessible. You can find it on Wikipedia if you like. Okay, so we now have all the ingredients for the proof. Okay, so let's start the proof. So to assume now that you have some graph now I will go back to the original amplitude, okay? Plus or minus 1. No, sorry, I won't go back. This is in a moment that we'll do that, but not now. Okay, so suppose we have that. Well, we do have that the degree is greater or equal than the largest eigenvalue of any tilde matrix I can make with plus or minus 1, as long as I only put anything different than 0 whenever x is connected to y in the graph G. Okay. However, this is greater or equal by the interlaced theorem that lambda of 1 plus 2 to the n 2 to the n minus 1 plus 1 sorry, 2 to the n minus 2 to the n minus 1 plus 1. Yes, so because AG is a subgraph of this graph. This graph has so its adjacency matrix has size the cardinality of Z in this direction. So its matrix is cardinality of Z here, cardinality of G here. Okay, and the matrix of this is 2n and this is 2n. Okay, so this is 1. So I is 1 here. And what is K? K is 2 to the n, which is the larger matrix. And L is the smaller matrix coming from G, which has at least this size. So we have this thing, and this is A of G. So what we're using this code. Sorry, H tilde or F2n, or in the case H tilde of n. So recall that we define A of n to be the adjacency matrix of F2, and H tilde is just some signed version of it. is when I put some number status here. That could be between -1 and 1. We don't know. Okay. So, but the Cauchy, so what we showed is that, well, this is greater equal than this. That was the claim tilde. And then the Cauchy interlaced theorem is that. Okay. And but what this is, we can make this cancels with this, and this is just 2n minus 1. So basically, what the only thing I have to create now is an optimizing game here, is to choose plus or minus ones or thetas between -1 and 1 to put in here, so that to make the largest eigenvalue here, the true n minus 1 largest eigenvalue exactly square root of n, or greater or equal than square root of n. If I can do that, then I show the result. Okay, and here's how we do it. Define a claim. Let's build a tilde n inductively by this process. Okay. I is the identity. So this is a 2n by 2n matrix. This is a 2n minus 1 by 2n minus 1 matrix. And this is 2n minus 1 by 2n minus 1 identity matrix. So you create it like this. Okay, inductively. Okay, so define a tilde n. So define a tilde n like that. Like recursively, that would be the better word. Maybe that's not completely right. But in any case, and then you can see exercise is that if this is one possible A tilde or the adjacency matrix of F2n. Because its adjacency matrix is exactly this matrix, but without any sign changes, without putting minus. If I don't put this minus here, just put the plus and create that recursively, then that's the adjacency matrix of Fn. Okay. So let me put as an exercise. An equals this moduli of Aij tilde. I mean, An if it exercise An equals An An. Oh, this is -1, sorry. And so if we can show that this is the adjacency matrix, this is just some sign adjacency matrix. And that the claim is that the eigenvalues of An tilde is exactly square root of n with multiplicity 2 to the n minus 1 and minus the square root of n with multiplicity 2 to the n minus 1. And that's if that is true, then the 2 to the n minus 1 largest eigenvalue of A tilde is the square root of n, and that's done. Then this guy is greater or equal than square root of n. Okay, why is that true? That's actually pretty simple. Because if I just square it, you can show by induction that this is always n times the identity. Okay, it's a simple induction argument. You show that this is n times the identity. Well, if that is true, that's obvious that the only eigenvalues are square root of n. And what's the multiplicity? Well, another induction argument shows that the trace, well, you can see what's the trace of this. You will see the trace of this is the trace of that guy, and this gives some value, this gives minus a value, so it's always 0. So the number of plus the square root of n has to be equal to the number of minus the square root of n. And so that proves that. And that finishes the proof. Okay. It's a very tricky, not tricky, it's a very like magician's move sort of a proof. Everything was known already. It was just arranged in a way to give the correct proof. So yeah, you could say that this is not a proof that introduces new methods and so on, although it's a very pretty proof. I don't know exactly why it's on the end of the mathematics. That's for another discussion. But you can ask that question, why? Which is not a problem. You can always ask those kind of questions. And I don't know the answer here. Although it's a very nice proof, you could argue why it's published on the end. In any case, we finished this very nice result. And now, well, we still have a gap, which is the Gottman lineal, to translate things about graphs into things about Boolean functions, which is a very sort of a nice, this introduces a nice idea. And the proof is actually pretty simple. Let me give here pretty quickly. So here I will assume, I will go back to the plus or minus 1 Hamming cube. So assume that the degree of f is n. So here I'm proving the A implies B, that properties about graph implies properties about the function. So assume for now that the degree is n. Then you define this function here. Okay, and so the graph you're going to choose is exactly the set of points where G is 1. And you will notice that the expectation of G is exactly f hat, because I multiplied by this, is exactly f hat of this, the full set. And since the degree is n, this has to be non-zero. Okay, but what is this? Well, this is exactly the number of points, which is 1, and then minus the number of points, which is minus 1, and divided, so this is 1 over 2 to the n. G is 1 minus G minus 1. And since this is not 0, that means that the size of G is not 2 to the n minus 1. Okay, so we are in the setting of claim A. And what you notice here is that what is the sensitivity of G at any point? Okay, well, that is n minus the sensitivity of f at any point. Because here I'm flipping everything around. This yes, if the sum is even, then I'm putting plus 1 if it's odd, and I'm putting minus 1. And so I'm flipping everything around. So if I flip one guy here, then that's what I want to do. I think I don't want to put this function here. I think the function I want to put is actually not this, sorry. It's actually x1, x2, xn. Let's see. What's the expectation of f is actually this guy. Yeah, now it's better. So then clearly you can see that. Okay, clearly you can see that you have this because I'm flipping every single guy here. And so, so whenever I change something here and it changes in F, you also change here. And so it will stay the same. And whatever change in F, whatever variable I flip in F that doesn't change the variable, will flip here and will change the variable, the value here. And so you have this. Okay, so you have these things. But also, if you look at the graph of G, if there is a neighbor has to be a guy which is only distanced by 1. So if I'm flipping this one variable. So if there is a neighbor, and this neighbor is in G, so then the value of G doesn't change. Okay, so therefore the guys which are not neighbors of some point X exactly tell you the number of guys which are not neighbors at some point X exactly tell you the sensitivity of G at that point. So this is also equal to n minus the degree of G of X at G. Okay, so that implies that the sensitivity of X equals the degree of X at G. But we do know that there exists some X0, this is by A. There exists some X0, should be made like X0, such that X0 of F, which is equal to the degree X0, is greater or equal than H of N. That's a supposition. Because now you're dealing with a graph that doesn't have this number, so it's satisfying the conditions of A, and then that implies that. But this is what? This is equal to the degree of F. If N is the degree of F. And that's less or equal. So that implies that the sensitivity of F is greater or equal than H of the degree of F. Okay, so but now if the degree of F is some M which is less than N, what we do, we just define this F tilde. I mean, we can assume that the monomial x1 times x2 up to xn is in the linear, the multi-linear expansion of F, and that's one of the guys with largest degree. And then I do that. Okay, and so the degree of F tilde is going to be M. And so F tilde hat at M is not 0. And so I can apply the same construction as before. So the sensitivity of F is definitely greater than sensitivity of F tilde, because F is this some reduction of F. But then by the previous result, that's greater or equal than H of M, because now F tilde leaves in HM, and then you apply the previous thing. But this is, well, this is equal to the degree. Okay, and that shows this. So basically, is if you assume the degree, then do something tricky, and then if it's not, then you reduce to that case. Now I want to show that B implies A. So suppose, assume by contradiction that degree of G is less than H of N. Okay, so I'm assuming that B is true, and then suppose I have some graph like that. So then I take G to be 1 if X belongs to G, and minus 1 if X does not belong to G. And you can see here like the coloring idea, the idea to use map Boolean functions as a coloring of the graph. Think of Boolean functions as a coloring of the graph. And then you define f of x to be x1 to xn, say g of x. I mean, you're kind of doing the previous proof backwards. But then you know that this is true, or sorry, f, but also this is n minus the degree of g, and so the degree of x equals the sensitivity x of f. And well, but then you know that for every x in G, the sensitivity of x, which the degree, well, the degree is a maxima. This is less than h of n. And also for every x outside G, because you can do the same with the complement of G, the same construction holds, and you have the same thing. And so you have that for every, yes, so this is for every x in G, you have this, and for every x outside G, you can do the same construction. You also have, this would be G complement, and so that would be less than h of n. And so that would show that well, however, there exists, yes. However, there exists some x, say, again, x naught, such that x naught of f is the sensitivity. And now we are assuming B, sensitivity is greater or equal than h of the degree of f. And so you are concluding that h of n is greater than the degree h of the degree of f. Correct. However, this shows then the degree, because the function is increasing, is less than n. And so if that is true, then f hat of n must be 0. But that's not the case, because f hat of n is the expectation of g, and the expectation of g is not 0, because we are assuming that the cardinality of g is not n to the n minus 1. Okay, so it's basically the previous proof backwards. This is absurd, or the contradiction. Okay, so again, then this finishes the proof. So the basic idea here is just that if you look at the function as a coloring of the graph, then that's why the Scotsman linear thing works. It's just a very nice idea, a very nice way to look at function. Then you can connect properties, like you can connect things from graph theory to results in Boolean functions. And this is like a few instances of such a case. And I hope you enjoyed this class. And that's it for today. Thank you.